Thanks for the chance to show you one stochastic model of infectious disease. I think this is not work solely by me, but also with another PhD student from our group and a postdoc who unfortunately cannot be here, but I'm the one who has the pleasure to present to you. I think most of us, the pandemic hit us, and then we start doing epidemiological modeling. Nice. We love epidemiological models, and we did a lot of them, bunch of them, because we were involved in different consortia, and some of them, they used case count data. Some of them started to using wastewater data because people thought, okay, it would be really nice if we can use the wastewater to see how many infections are really there in the population, not only how many go to tests and getting reported. And then we started thinking, okay, now we have both data sources, so let's build a model that integrates both of them. And this is quite a challenging thing, and today I just want to show you what's the first part of the model, so the case count data model. We also have already done the second one, but that would be too much for 10 minutes. So let's look a bit about what our transmission model is, our ascertainment model, and how do we want to fit this to data we have at hand. So we're starting up with what is most important, the number of infections. Stuff we don't see, but which is there. The number of infections, we say, okay, this is somehow Poisson distributed depending on our force of infection and the reproduction number of the disease. The reproduction number can change over time, so this might be Brownian motion, having some drift going up or down, depending on which stage we are of the disease, which prevention measures there are. And the force of infection is a weighted sum of how many people were already infected over the past 2 weeks. So how large is the force of me getting infected if I meet other people. Having the number of infections as a Poisson distributed random variable, we then can point from this number of infections to the next number of k days at which these infections might get potentially reported. So at which days people showing symptoms, at which days they then test themselves, and if they test themselves, there's a binomial distribution that this test is positive or did they already test, and so we end up with what we would observe, the number of reported infections. So this is the general modeling setup. So several steps, and what we then take as a state space are these 3 boxes. So number of infections per day for the last k days, the infections which are then potentially reported for the last k days, and the number of reported infections for the last k days. So 3 times k setting to 2 weeks make up like round about 42, 41 hidden variables which we need to fit later. There are some parameters also involved here. This weighted sum for the force of infection and the multinomial we take as the discretized gamma distribution, because we argue kind of that it's likely that symptoms occur after some days. So let's say between day 2 and 3, and then people are most likely to get tested and getting reported, and then it decreases again. And nearly no one directly tests when they get infected because they don't know yet. So there we have a shape and a scale parameter for this distribution which we want to learn, and we want to learn this binomial parameter there, making up 3 parameters we want to fit with the state dimension of 41 in this case. And how do we do this? So in general, Bayesian inference for hidden Markov models, in this case, or hidden dynamic models, one way to do so is particle filtering. And the idea there is that we have hidden dynamics, our x, which is the state base of 41 different state variables. We have some kind of a transition law, so we know how to proceed from one time point to the next time point given the parameters, and we have some kind of readouts, and now we kind of know how they are, we have assumptions how they are related to our state space. And then in order to do Bayesian inference, we need to get the likelihood, and what this means is we need to calculate the probability of observing a data sequence given our parameter vector, and this means we need to integrate all possible unseen trajectories of these hidden states. So a lot of simulating and integrating out would be involved there, and the general idea how one can do is a particle marginal metropolis Hastings or particle marginal MCMC methods, and they sample a parameter as you would do in a normal MCMC method, and they then approximate this likelihood by saying, okay, we take a number of particles at xt, we propagate them forward based on this transition law which we know, then we weight them based on how well they match our data, and having weighted them, we can resample them. So we don't propagate forward everything to the next time step, but only what was a nice trajectory, what fits our data well will be then used to propagate to the next time step xt plus 1, and then we start over and over again. So at the end we end up with trajectories, and many trajectories, so and many possible hidden dynamics, but all of them are already in such a way that they kind of sorted by nicely fitting the data, and the sums and multiplying up all these weights then gives us an estimate on for this likelihood, actually an unbiased estimate, which is quite nice. So we can use this then in the Metropolis Hastings algorithm and accept or reject our parameter theta and get a new parameter, sample new, do a new particle filter one, and so on and so on. So this is quite an intensive task to do. This is why Julia is quite nice, because this involves a lot of forward simulation steps, and this is where Julia is particularly fast in. So it's really something we don't want to do in Python. Having done this, the results look like that. Not good. So we get some kind of approximations of our posterior distribution of the parameters, and the 90% confidence interval cover our true values, but the distributions don't seem to be correct yet, and they seem kind of skewed, so there might be some structural things in there. But so we were starting to think, okay, how can we maybe inform this a bit better, because what we have this one area of case counts, but a huge dimension of states and a huge and some parameters we need to fit to this just one dimension of observables. So the idea is, in this forward step that the particle filter does, we want to inform this forward propagation step already by the next data point, so that we, when we do resampling by weighting, don't put as many particles into the trash as we do right now, but we can reuse and get more unique trajectories, which then gives us better estimates. So we want to add somehow the distribution of the next hidden state given our next data point into this propagation step. And since we don't know this distribution, the idea is to use the neural network to learn this mapping or to learn this distribution, which we can then add on top of this particle filter. Right now, we're just trying to learn the mean and covariance metrics for a normal distribution there. Of course, given our model formulation, we should maybe add some different assumption here, but this is what we right now try to achieve, to make some kind what we call then simulation-informed neural network to generate posteriors with the guided particle filter. And to our knowledge, this is kind of new. So yeah, that was all. And if you have any ideas how to maybe improve this even more, or to use a different framework for the inference, let me know. I'm happy to take any suggestions and questions on that. Thank you.
Thank you. Any question? Yeah?
Thank you for the talk. Clearly very relevant and similar, right? You use similar methods. This PMMH, particle, what was the abbreviation?
Particle marginal Metropolis Hastings.
Particle marginal.
Because you use a particle filter to
exactly.
approximate the marginal likelihoods in the Metropolis Hastings.
Would you say that would be useful anytime you have many agents and parameters for each? Kind of, that sounds like that was the point, that it would take too long to use just normal MCMC because there's so many, or is it wrong?
The point is, it's useful if you have this kind of hidden dynamics which you don't know.
Yes.
So, and you want to integrate them out. But as soon as the hidden dynamics grow, this gets really, really slow. So
this gets really, okay.
So I in my experience, it doesn't scale that well with the number of states-based dimension as we would like it to have. So like having this dimension of 40 to 50 is already quite big. I tried it with 500 and it ran forever.
Okay. All right, I'll ask you more about this later.
Yep, sure.
Someone has questions.
Thanks.